share my screen. Perfect. And that's the wrong class. Oop. All right. So yesterday we talked about current. Okay. So thus far we've been hearing about potential difference or voltage. Now current. Today we're going to be looking at resistance, and all of these concepts are going to play a part in what's called Ohm's law, which really states that anything that abides by Ohm's law means that the current that passes through that substance is going to be proportional to the voltage across 2 points on that substance. So think about, we're going to see some examples of substances that follow Ohm's law. We're going to see some examples of substances that do not follow Ohm's law. So we're going to be able to calculate resistance, which kind of the idea of resistance lends its hand to light bulbs, like you see here. Not necessarily these types of light bulbs, but more of the filament style light bulbs, which are starting to go by the wayside a little bit. Trying to get into longer lasting light bulbs, which I still debate that the LEDs that they sell us do not last as long as they're supposed to, but that's just me. But what resistance is the opposition presented to electric current by a material or device. The SI unit for resistance is the ohm. Okay, that's the omega symbol, I believe. I'm not really up to snuff on my Greek. I don't even know if it's Greek, but it's equal to 1 volt per ampere. You can calculate it using the following formula. Resistance denoted with a capital R is equal to the potential difference divided by the current. So these 3 concepts play a role in what we do in chapter 18 as well. We're talking about circuitry. So you want to make sure that you've got these down pat. And for many materials, as we said, resistance is going to be constant over a range of potential differences. These are what they call ohmic materials, like copper, aluminum, all right? Also, the Ohm's law doesn't always hold for all materials, light filaments, diodes, okay? You think about what the differences between those are, okay? When we have aluminum or copper and it's got electricity flowing to it, you don't necessarily see a result of that process. Okay, you get copper, looking at any type of wire or metal surface, and there's electricity running through it, it doesn't look any different. But when we start looking at light filaments and diodes, you notice that when electricity starts to pass through them, they begin to glow. And so you start to see the differences between ohmic and non-ohmic materials. Now, the idea of resistance is going to be dependent on a few things. The length of substance that the current is going to be passing through, the cross-sectional area, the temperature, and the material. You can take a look at these kind of factors on page 613, table 2. In fact, I encourage you to do that just so you can see how all that plays into a level of resistance. Now, we have resistors kind of all over the place. What they do is they are used to control the amount of current in a conductor. Salt water, perspiration, all lower the body's resistance. One of the main things, or main reasons why, in a thunderstorm, you don't want to be found in water. Okay? First off, salt water obviously contains what? Salt, yes. And going back to chemistry days, what happens when a salt gets dissolved in water? They break down into their ions. Starting to come back. And what are ions but charged particles? What's really electricity but a movement of charged particles? So we start having dissolved substances that are ionic in nature. You're going to have a really easy pathway for electricity to propagate. Okay, move along. So that's why it's not confined to just oceans. You know, in almost any body of water in nature, you're going to have ions present in the water. Because, I mean, there are various types of salts. You have various types of runoff from the ground. Okay, so you're going to have some sort of ionic concentration in these natural bodies of water.
Why, like if there's a thunderstorm at sea, way out there, and lightning strikes the water, why doesn't the charge travel into land? Or does it? It's just like weakened because
you got to think about it, because it does go outwards, and so as you're saying, most likely it does dissipate. Plus you're going to encounter various resistance depending on where it strikes. You know, there could be platforms out there we don't see. There could also be other animals that are absorbing it. So there's also a difference between, you know, current and voltage of what's going on there, and so that plays a role in all that stuff. So I'm assuming there's gonna be a lot more than I'm just mentioning right now, but those are all some scenarios that would not, you know, lessen it over a greater distance. Okay. Potentiometers. It's a fancy word for basically like volume controls, dimmer switches. Okay. Mostly like the rotary ones. I know Mr. Cervek's class has those switchboards on a lot of the tables. Those are all examples of potentiometers. Or if you have a light dimmer at home, okay, that's adjusting the amount of resistance that is going to be going through that circuit. So let's look at calculating resistance, shall we? The resistance of a steam iron. Let me move some of my stuff here. The resistance of a steam iron is 19.0 ohm. What is the current in the iron when it is connected across a potential difference of 120 volts, which is basically your standard voltage of an outlet at your home? Okay, so go to my oak yolk dam. And again, what do we know? We know that resistance is 19.0 ohm. Yes, I make some great ohmic symbols there. We know that the potential difference is 120 volts. We need to solve for I. So taking the equation R equals delta V over I and solving for I, we're going to have the new formula delta V over R, and we can simply go ahead and plug in our numbers here. 120 volts divided by 19.0 ohm. And again, if you have your calculator handy, you should get 6.32 amps. I know it's a little more difficult than it was yesterday. Oops. Now I want you to open up for more practice, page 615. Well, you know who doesn't have their book today, right? Exactly. Could be. Could be. Even if he had his book with him, it's still not present. Okay, so page 615. Let's look at let's look at number 4. The first 3 are pretty similar to what we just did. I'm trying to come up with other ones that, you know, solve for various variables. How about that? Number 4, the current in a microwave. Let me try to get this over here. The current in a microwave oven is 6.25 amps. If the resistance of the oven circuitry is 17.6 ohm, what is the potential difference across the oven? Okay. So again, we know our current, 6.25 amps. We know our resistance, 17.6 ohm. We need to know our delta V. So R equals delta V over I. We need to solve for V. So we're going to have both sides multiplied by I, to where we get R times I. Then we just plug in our values here. Resistance, again, 17.6 ohm times our current, 6.25 amp. And we should get 1.10 times 10 to the second volts. That's how we solve for volts. Now let's look at 5. Number 5 says a typical color television draws 2.5 amps of current when connected across a potential difference of 115 volts. What is the effective resistance of the television set? So again, current 2.5 amps, potential difference of 115 volts. No changes to this equation this time. So we get R is equal to 115 volts over 2.5 amps. We should get 46 ohm. Questions on this? Very difficult, right? Very difficult. Okay. So, for your homework, you are to do problem bank D, which should be posted to the classroom, 1 through 10. Okay? Again, that's problem bank D, 1 through 10. And that is due Monday. Unless you get it done sooner, then you can go ahead and feel free to submit it. Any questions from those of you at home? If you can, you don't have to say anything if you do not. Well, alrighty then. You can go ahead and start working on your homework.